Okay, so let's talk in more depth about this 1D problem. So first let's talk about some of the math preliminaries. We'll then go into what's called variational methods, a more general approach to solving these problems. And for the project description, we'll talk about this in class. So 1D linear spring. Okay, if you recall back, we had this bar. We put a load on it on the end here, and we're going to divide this bar up into two elements. Okay, so we have a spring here and another spring. We're saying that the spring constant K1 and K2 may vary. This allows you to look at, let's say, if you had a region that's copper, maybe a region here that's steel, these are bonded together, you could look at variation of material properties. So here is our basic constituent model. If you apply a force, and that should not be K, that should be a force F. So I'm applying a load F on the end of this. So I have my force equals the spring constant and some given displacement. So if we take this first element out, we apply a F1 on this side, F2 on this side, and those forces correspond to a displacement delta 1, displacement delta 2 at these points. So for that element, here's my constituent relation. My force 1 is the spring constant K, where that K is actually K1, and then it's a relative displacement. So delta 1 minus delta 2 gives me the force. Just recall, if delta 1 is equal to delta 2, we just have rigid body translation, and that would result in zero force. Alright, so if we think about these forces here, at equilibrium, the force at 2, F2, must be equal and opposite F1. So we can take the same expression and write it in this form. So I've just put a minus sign in front here. Now I have two equations, F1 and F2, based on this one element. I can put that into a matrix. So if you multiply this out, the first equation is here, second equation is here, and I can also put this in a matrix form. So here you've basically set up a finite element problem, okay, for a single element. In practice, you're going to know either a force or a displacement at this point, and you're going to solve for a force or displacement at this point. So in all these problems we do, whether it's mechanics, 1D, 2D, 3D, you're going to know a set of displacements, a set of forces on a surface, or if it's temperature, which we'll get into in a minute, you have a similar set of knowns and unknowns. That allows you to solve for the unknowns. For example, if we applied F2 here, delta 2 would be unknown, and let's say we constrain delta 1 to be 0. In that case, your unknowns would be F1 and delta 2. So you have two unknowns, two equations. You can find those. Another example, thermal problem. This is set up identical, where you have thermal resistance in each layer. So we can define an element for K1, 2, 3, and 4, where these K's are thermal conductivity. And let's say if we just take the first element, thermal conductivity 1, you have heat flow Q1, heat flow Q2. In this case, one critical thing is we're defining heat flow as going into the element, and we use that to set up the finite element problem. So if we go ahead and come to Fourier's law, here's my local heat flow, lowercase q, here's the thermal conductivity over some area, and is proportional to a thermal gradient. So temperature dt over change in length dx. So for a uniform layer, remember we discretize this equation. So now you have a delta T over L of that given element, or length of that region, with uniform thermal conductivity. And my heat flow is simply defined here. Okay. Similar to a force balance problem, energy conservation requires the heat flow coming in one side must be equal and opposite the other side. Otherwise, you're going to have heat generation internally. So we have Q1 equal and opposite Q2, so we have this relation, just a minus sign difference. So you can put this into a matrix, Q1, Q2, based on these two equations. And very similar to the 1D bar, in that case you knew force or displacement at a point. In this case you're either going to know the heat flux going in or the temperature. Or typically you know the temperature at the 2 points, and then you can solve for the heat flow. So a few questions to think about is, what happens when you have multiple layers? How do you construct this? What will be the size if, let's say, you have two different materials bonded together? How would you solve this? What would the matrix look like? Another example that we'll talk about is chemical diffusion. You notice this equation looks very similar to our Fourier law. If I come back up here, you have this for thermal gradients. Same thing applies if you have a chemical gradient. So here's my chemical potential and a diffusion coefficient, and this gives rise to flux of concentration. So the governing equation for time-dependent problems is a rate of change of concentration. So this is a time rate of change of concentration is equal to the divergence of the flux. So in 1D, that's just the negative of my flux in 1D. So dJ dx. And this gives Poisson's equations.